Modern high-performance microprocessors now pull hundreds of watts of power. This energy concentration creates intense, localized hotspots on the silicon, pushing power densities toward an extreme 100 watts per square centimeter. To keep the chip from destroying itself, that heat has to escape. It travels through a multi-stage pathway, radiating off the active silicon die, moving into an integrated heat spreader, and finally exhausting out through the main heatsink. This animation shows the total thermal resistance formula for that cooling pathway. Notice the variables for TIM1 and TIM2. These are the thermal interfaces, microscopic gaps between the silicon, the spreader, and the heatsink. We usually fill these gaps with thermal paste, but those layers become massive choke points. At extreme power densities, traditional thermal paste stops working as a conductor and starts acting like an insulator. The paste alone can cause temperatures to spike by up to 30 degrees Celsius, severely throttling the entire system. Liquid metal offers a vastly superior alternative. It has sub-zero thermal impedance, meaning heat passes through it almost instantly. Right now, applying liquid metal is mostly a risky, aftermarket modification done by PC gamers chasing maximum performance. But you cannot simply trap a liquid inside a high-performance server. The physical reality of computer chips is that they bend while they operate. When silicon and packaging substrates heat up, they expand at different rates. As you can see in this animation, this fluctuating temperature causes the actual gap between the die and the lid to constantly change shape. As the physical gap shrinks under this mechanical stress, any liquid metal trapped inside is violently squeezed out of the edges. This leakage leaves an incompletely filled interface. You end up with dry spots sitting directly over the hottest parts of the processor, guaranteeing a critical hardware failure. To safely utilize liquid metal at an industrial scale, engineers have to solve a seemingly impossible paradox: perfectly sealing a liquid inside a container that is constantly changing its own volume. Engineers have designed a new hardware solution called the LM lid and LM heatsink. These packages treat the thermal interface as a dynamic fluid system rather than a static seal. This schematic shows the core innovation. Instead of flat metal plates, these lids feature a built-in reservoir structure, acting as an internal tunnel directly above the processor. A pre-compressed rubber seal ring surrounds the chip, containing the liquid metal without rigidly locking fragile components. Here is how those parts assemble into a complete package. It provides whole liquid metal connections across the entire cooling stack, creating distinct fluid pathways for both TIM1 and TIM2. This internal geometry transforms the hardware's function. The lid acts as an automated fluid regulation system. Here is how the system breathes. When the chip cools and warps downwards, the shrinking gap forces excess fluid safely up into side reservoir chambers. When it heats and warps upwards, the gap expands, and the reservoir releases fluid back down to perfectly refill it. This dynamic breathing cycle ensures the gap remains completely filled with highly conductive liquid metal at all times, eliminating those dry, dangerous hotspots. There is a secondary benefit to this design. The pre-compressed rubber seal acts as a soft connection. As this schematic shows, rigid packages often suffer from cracking and delamination at the die edges. The soft connection absorbs that mechanical stress. The breathing reservoir elegantly solves the thermal leakage and the mechanical stress problems in one unified design. This chart measures the impact. At a power density of 100 watts per square centimeter, traditional paste, the tall red bars, causes a massive 30-degree temperature rise. But the whole liquid metal connection, the tiny blue bars, keeps that rise to a mere 2 degrees. That nearly 30-degree drop allows computer processors to run indefinitely at their maximum clock speeds without facing thermal throttling or early physical degradation. By slashing the thermal resistance of TIM1 and TIM2, the system removes a major barrier to peak performance. Because the leakage and reliability issues are solved, liquid metal moves from the personal rigs of enthusiasts into the industrial mainstream. This technology is now viable for mission-critical deployments. That includes heavy-duty AI data centers running continuous operations and rugged automotive systems that demand absolute reliability under constant physical vibration. By designing hardware that breathes in harmony with the physics of the chip, engineers have solved the warpage paradox, clearing the thermal roadblock for the next generation of computing power.